Okay. So we're going to go to number 4 first, because number 4 was actually a word problem I gave you at the end of class yesterday, but we didn't have time to finish it. So this is actually the same problem I gave you in class. So let's see how well you guys did. Then we'll go back to answer number 1, 2, and 3. Because 5 and 6 are sex-linked problems, I'm going to wait till a couple days from now to go over them, because I haven't taught you sex-linked traits yet. So you may not have done it right. So it's not worth going over yet. All right, so let's go and begin. If you have any questions, this is the day to ask. In corn, purple kernels are dominant over yellow, and smooth kernels are dominant over shrunken. An ear of corn has 381 kernels. These values here are your observed quantities. So for phenotype, we have purple and smooth. We have purple and shrunken. We have yellow and smooth. We have yellow and shrunken. The observed is 216, 79, 65, and 21. That total it provided you was 381. Now, there's a couple ways that you guys can find the expected. I'm going to show you both ways. First way, your prediction would be the kernels are the result of double heterozygous cross with a ratio of 9 to 3 to 3 to 1. What is 9 plus 3 plus 3 plus 1? 16. So one way you could find, and I honestly doubt any of you did this, but I want to show you a new way, is 9 divided by 16, 3 divided by 16, 3 divided by 16, and 1 divided by 16. If you did that in your calculator, here are the frequencies that you would get. 0.5625, 0.1875, 0.1875, and 0.0625. I honestly doubt any of you did that. Here's why I hope you at least did. It says the parents are heterozygous for both traits. So both parents look like this. So I told you yesterday, if you were to do an actual dihybrid cross with 16 grids, I'm going to look you in your face and tell you you are crazy. You're going to waste about 8 minutes that you can avoid wasting. Instead, do 2 monohybrid crosses. All right. Both of these had the same outcome, guys. What's the frequency of getting a dominant trait? 0.75. What is the frequency of getting a recessive trait? 0.25. So the 9 to 3 to 3 to 1, that ratio, the 9 represents a dominant trait with another dominant trait. So you would do 0.75 times 0.75. What does that equal? 0.5625, same one I did earlier. Dominant to recessive, 0.75 times 0.25 is 0.1875. Recessive to dominant is 0.75, or excuse me, 0.25 times 0.75 is 0.1875. And then recessive to recessive is 0.25 times 0.25 equals 0.0625. So no matter how you did it, whichever strategy you wanted to do, the frequencies are the same. Are there any questions yet? All right. So with that being said, are these numbers your expected frequencies or your expected quantities? Right. We need quantities. So how do you find the quantity from the expected frequency? You multiply the total by each of the respective frequencies. The total is 381. So now I need to hear your voices. This is basic algebra. What is 0.5625 times 381? 214.31. What is 0.1875 times 381? 71.44. 60, same one for the next. And what is 0.0625 times 381? 23.81. Great. So let's plug those into the table. That was the quote unquote hard part. Everything else should be smooth sailing. Just have to complete the chi-squared equations. All right, so let me hear you. What is 216 minus 214.31? 79 minus 74.71.44. 65 minus 71.44. I like the participation. Keep it coming. 21 minus 23.81. Okay, now we have to square. And what is 1.69 squared? What is 7.56 squared? What is 41.474? Oh, I'm sorry, I said that weird, didn't I? What is negative 6.44 squared? I said the answer. Yeah, 41.474. And what is negative 2.81 squared? Now, if your answer is different from mine by a tenth or maybe two hundredths of a point, that is not going to be a big deal. It's not going to affect your chi-squared. All right, finally, you divide by the expected. 2.856 divided by 214.31. 0.013. 57.154 divided by 71.44. 41.474 divided by 71.44. And 7.896 divided by 23.81. And you have to do the sum of all that. Remember yesterday I showed you sigma. Sigma means summation. What is the summation of those four numbers? I got 1.725. Okay, so your chi-squared value is 1.725. How many different outcomes for the p's are there? 4. How many degrees of freedom is that? 3. You always take your total number and subtract it from 1, or subtract 1 from it. So you have 3 degrees of freedom. If you went to the top of your worksheet, what is the critical value for 3 degrees of freedom? 7.81, right there. That is your critical value. So when you were asked, does the data fit your predicted phenotypic ratio? That's another way of asking, do you accept or reject the null? Yes or no? So does the data fit your predicted phenotypic ratio? You would say yes. Chi-squared is less than your critical value. So in this case, you would accept the null hypothesis. And if you don't understand the null hypothesis, I'll explain it one more time. Tyler's sitting in that desk right now, and a little newspaper clipping I had on that column fell down. The null hypothesis states that those two factors, Tyler sitting where he's sitting and that newspaper falling, are totally unrelated. If you accept that, then you're saying, yeah, that the fact that that thing fell down and he's sitting there happened by pure chance. Or you can reject that. You could, and that would mean it didn't happen by chance. Those two things are connected. Tyler sitting there is the reason why it fell down. Maybe. That's what it means when you reject the null. You are saying it didn't happen by chance. When you accept the null, you're saying it did. Logan is sitting right there, and at the very same time, the World Cup started for America. Are those two things tied together, or are they not? If you accept the null hypothesis and you're saying Logan's sitting where she's sitting, and the World Cup with USA versus Iran, those two things happening at the same time, no connection. If you reject it, then you're saying there is a connection between the two. Okay? All right. Any questions on number 4? Nah? Well, let's go to number 1. And then we'll do 1, 2, 3. Tyler, you remember your question yet? It's lost. It's lost in there. All right, here we go. 1 and 2 are kind of like the warm-up problem I gave you yesterday. In pea plants, yellow seeds are dominant over green seeds. In a cross between two plants, both heterozygous for seed color, the following was observed. All right, so let's write down some of the stuff they gave us. We got yellow, 4,400, green, 1624. First question, what is the sum of 4,400 plus 1624? Okay. Now we need to figure out the expected. We have to go with expected frequency first, then expected quantity. So, guys, it says both parents are heterozygous. They look like this. What are the odds that that cross would produce a dominant phenotype? 0.75. And recessive would be 0.25. And we'll remind you once again, in this problem, I'm going to say this very calmly, but very directly to all of you. You have a choice between yellow seeds or green seeds. When you are given two choices, is it always 50-50? No. Do not fall into that trap. It is clearly not 50-50. This is 75-25. It's based on what the parent's genotype is. All right? So you take those frequencies, you multiply it by the total. What is 0.75 times 6,024? 4,518. And what is 0.25 times 6024? 1,506. Let's put those in here. That's the quote unquote hard part. Everything else should be cruise control. What is 4,400 minus 4,518? And what is 1624 minus 1,506? What is negative 118 squared? 13,924. Same goes with the bottom one. All right. What is 13,924 divided by 4,518? 3.08. What is 13,924 divided by 1,506? 9.25. What is the summation of those two? 12.33 is your chi-squared. How many degrees of freedom are there in this problem? There's 1 degree of freedom. You have two possible outcomes. 2 minus 1 is 1. What is the critical value for 1 degree of freedom? And by the way, when you're looking at a big, ugly table for chi-squared, what p-value do you always look at? 0.05, 5%. All right, so there's your chi-squared. Do you accept or do you reject the null hypothesis? You reject it. So does the data fit the predicted phenotypic ratio? No. No, it doesn't. Chi-squared is greater than your critical value. You reject the null. I want to translate that for you if you still haven't caught on. When you reject the null, you are saying that getting this observed outcome is not statistically possible by chance. This outcome is influenced. It is directed. It didn't happen randomly. Maybe there's something going on with the way that the gardener is planting his peas. I don't know. It's just not going to happen by chance. Any questions on 1? Let's move on to 2. I want to make sure you guys got the genotypes right for this one. You might have gotten a little lost. In peas, smooth seeds are dominant over wrinkled seeds. In the pea generation, by the way, pea generation and the fact that we're using peas is just a complete coincidence. The pea generation means parent generation. It's your original generation. In the pea generation, you have a homozygous smooth seed is crossed with a wrinkled seed. So what are the genotypes of the two parents in the pea generation? It doesn't say heterozygous. It says homozygous for smooth is crossed with a plant with wrinkled seeds. Homozygous dominant, homozygous recessive. The resulting F1 plants are crossed. Well, if you cross homozygous dominant with homozygous recessive, what will all the offspring be? Right. And it says clear as day on that next sentence, the resulting F1 plants are crossed. So you're going to cross heterozygous with heterozygous. The seeds of the observed F2 generation were smooth and wrinkled, 5474, 1850. So let's fill in some of these. What is 5474 plus 1850, please? 7324, thank you. All right, we have a heterozygote crossed with a heterozygote. So you've already done this once. What is the frequency of getting a dominant phenotype? 0.75 for dominant, 0.25 for recessive. You multiply those frequencies by the total. What is 0.75 times 7324? 5493. I'm going to go ahead and write that in the box. And what is 0.25 times 7324? 1831. Okay, that's the hard part. Now everything else is just basic math. 5474 minus 5493, negative 19. 1850 minus 1831, it's 19. 19 squared is 361. What is 361 divided by 5493? 0.0657. And what is 361 divided by 1831? I got 0.1972. What is the summation of those two? I got 0.2629. That's your chi-squared right there. That's your answer. Now I'm going to tell you on the AP exam, you might just be asked to find chi-squared and that's it. Just find chi-squared. It's going to give you multiple choice. A, B, C, D. Which one is chi-squared? Or it might be on the FRQ. Does the data fit the predicted phenotypic ratio? How many degrees of freedom are there? 1 degree of freedom. So what is the critical value? 3.84. Does the data fit the predicted phenotypic ratio? Yes. Chi-squared is less than the critical value. In this problem, would you accept or reject the null? You accept it. So when you accept it, what you are saying is that this observed outcome is statistically possible to happen by pure chance. There's nothing directing that outcome. There's nothing behind the scenes that's moving the parts. This is all just totally random. All right, finally for today, number 3. In flowering plants, white flowers are dominant over red. Short plants are dominant over tall plants. I don't know why the euro symbol is in there. Typo. When 2 double heterozygote plants were crossed, the resulting phenotypes were observed. So I can go ahead and write in a few things in the box here. Can you tell me what 206 plus 83 plus 65 plus 30 is? 384. Thank you. Okay, let's see how well you guys remember. What is the ratio when both parents are double heterozygous? 9 to 3 to 3 to 1. So do you remember what those frequencies are by now when you have a 9 to 3 to 3 to 1 ratio? And if you're unclear as to what the 9 means, the 3 means, the 3 means, and the 1 means, I'll tell you. The 9 is dominant, dominant. That first 3 is dominant, recessive. This 3 is recessive, dominant. And that 1 is recessive, recessive. So what is the frequency of 9 out of 16? 0.5625. What is 0.5625 times 384? 216. I'm putting it into the table. What is 0.1875 times 384? Because that's twice, I'm just going to put it in twice. And what is 0.0625 times 384? 24. Okay, great. There's the hard part. Now just everything else should be pretty easy. 206 minus 216, negative 10. 83 minus 72, 11. 60 minus 24, negative 7. And 30 minus 24 is 6. Negative 10 squared is 100. 11 squared is 121. Negative 7 squared is 49. 6 squared is 36. 100 divided by 216 is, and check my math, is 0.463. 121 divided by 72 is 1.681. 49 divided by 72 is 0.681. And 36 divided by 24 is 1.500. The sum for all that is 4.325. If you're off by maybe 1/1000th of a point, it's not that big of a deal. This is your chi-squared value. How many degrees of freedom do we have in this problem? 3. So what is your critical value at 3 degrees of freedom? 7.81. Chi-squared is 4.325. Critical value is 7.81. Does the data fit the predicted phenotypic ratio? Yes, because chi-squared is less than your critical value. And you would accept the null, which means that the observed outcome could happen randomly. So we have 5 minutes left. We're done with 1 through 4. I told you that if you wanted to try 5 and 6, more power to you, but I'm not going to hold you accountable for it yet. We'll go over Thursday. But to give you a little taste of sex-linked traits, I want you to go number 5. And if you try to set up a Punnett square, let's just see if you did it right. We'll do that for our last 5 minutes. So please go to number 5. If you mess this up, if your guess on how to do this is pretty badly butchered, don't feel bad. We haven't done it in class yet. All right, here we go. A female who's a carrier of the colorblind allele mates with a male who is colorblind. All right. So here's the female who is a carrier for colorblindness. Here's a male who is colorblind. I want you guys to help me as to what would be in each Punnett square. I'm going to take, or each box. I'm going to take it one at a time. I'm going to ask you 3 questions for each one, okay? Here we go. First question, what is the gender? Female, good. What is the genotype? Heterozygous. What is the phenotype? Here's your choices. Normal or colorblind? Good. Next one. What is the gender? Good. What is the genotype? Homozygous recessive. What is the phenotype? Very good. Now this is going to be tricky. You're probably going to butcher this. What is the gender? What is the phenotype? Normal. What is the genotype? You don't say homo or hetero with males. Males, when it comes to sex-linked traits, cannot be a carrier. They don't have 2 alleles, they have 1. So what do you call half of a circle? Semicircle. What do you call half of the earth, like northern and southern? Hemi. We call this hemizygous. And if it's a dominant allele, you're going to say hemizygous dominant. So that male is hemizygous dominant. That male, that's a male. What is the male's phenotype? Colorblind. What is his genotype? Hemizygous recessive. Let's go down to the cats. I got 2 minutes left. In cats, fur color is determined by the dominant, sex-linked alleles. When you hear codominant, does that mean intermediate of the two traits, or does it mean both traits are expressed? Both traits are expressed. Black and orange. A calico female is bred many times with a black male. They produce the following offspring. Here we go. Here's the female. Here's the male. Both traits are dominant, so you can't say dominant or recessive. You got to say it a little differently. Male or female? What color? What genotype? They're both dominant. B and O are dominant. You would have to say homozygous black. What is this? Male or female? Female. What color? Calico. What genotype? That's heterozygous. What gender here? Male. What color? Black. What genotype? Hemizygous what? Black. What gender? Male. What color? Orange. What genotype? Hemizygous orange. We'll go over 1 or 5 and 6 on Thursday.